Today we're going to talk about miniature tornado maker devices. Just joking, today's topic is magnetic stirring. If you ever had a big glass of water with loose tea and enjoyed the leaves turning inside? No? Just me? Anyway, I recommend you to try it. It's very calming. At least until the leaves stop turning and you have to stir it up again. If only someone would create a device that keeps the water turning. And someone did. In 1944, Arthur Rosinger patented a device that uses an electric motor to spin a magnet that spins a magnet. And the working concept didn't really change over the last 80 years. With today's cheap tech, it's quite easy to make one yourself. Even I made one with RGB neopixels a few years back. It even can be controlled via Bluetooth. Maybe I do a video on this another time. But the problem always was that the motor was too weak and my tea was getting cold. Never mind the flimsy housing. So I decided to get a stirring device with heating. But they all seem to be a bit pricey. Maybe the used ones are cheaper. How about broken ones? I mean, it's just heating and steering, can't be that hard to repair, right? I found one that said, heating relays not turning on, and I was like, yeah, I'm just gonna replace the relay and it will work. The price was good and repairing stuff is fun, so I choose to give it a try. While waiting for the package, I did a bit of research and found out that the device is quite old but from a reputable German manufacturer. This gave me hope that it would be repairable. I even found a circuit plan for a slightly older model that seemed to be almost identical with my model. After it arrived, it was quite dirty from 35 years of service, 35 plus years of service. And someone scrapped a A1 into it. Maybe it was part of chemistry class A1. Since I'm not sure what chemicals were in touch with this, I used gloves to clean those in. I wasn't able to remove all the dirt since some of it is quite burned in. But now I felt a lot more comfortable handling it. After finding a Heißgerätestecker to plug it in, I tested the spinny function. Spinning seems to work, even the speed controller works, judging by the sound. Sadly, no reaction from the heating switch. Now let's try it with a magnet pebble. If we add some water to it, we can maybe try to make one of those miniature tornadoes. It seems to work, but I think we need a bigger magnet pebble. Or do we? Let's add some color to see the tornado better. Wow, that looked better than I was expecting. I already like this device as a magnet stirrer, but now let's get inside and repair that heating function. Three or four screws went out quite easy, but the last one needed a bit more of torque to get loose. After removing the screws, I wasn't sure if I had missed something, but then I managed to pop it open.
Do you smell it? That smell. A kind of smelly smell. A smelly smell that smells smelly.
The first thing that hit me after opening was the smell. I assumed it's the old German electric motor oil in there. It's like the smell of an old book mixed with the smell of a transformator station. Look at it, it looks a lot better than what I have expected from a device of this age. But I guess it's from a time when Germany was still famous for high quality machines. Also, I didn't find any dirt inside. I guess the motor shaft seal is still working. While researching dirt and corrosives getting inside the housing via air cooling of the motor was named as the main reason why those stopped working. We're looking exclusively at through-hole components here, no SMD or such new age stuff to be seen. Here we can get a first glimpse at the optoelectronic speed controller. But what we need to fix seems to be up there, the relay. The motor is way bigger than I expected it to be, and it runs absolutely smooth. Over here we have a
full bridge rectifier.
Let's take a closer look at that optoelectronic speed controller. Here's the rest of the speed control circuit, but since that works, it doesn't concern us right now. Some of the connectors seem a bit rusty. At first glance, the trafo tells us the device is operating with 12 volts in some parts at least. In the heating circuit we can see an OMAM. Some of the connector pins were not gold plated, not sure why they left those out, but I have a theory about it. On one PCB we can see the date 1984. I guess this makes this device 38 years old. I removed the heating PCB and inspected it. After the first view I decided it was a bit dirty with flux and oil, so I cleaned it up a bit. I removed the relay only to find out it's still working. But when the relay is still working, it means there's something broken in the path before it. There aren't many active elements on here that can break. So my first guess would be the transistor that turns the relay on. So I ordered a few replacement transistors. While waiting for the parts, I decided to digitalize the old circuit plan into Kicad. Sadly, after a while I noticed more and more differences between the device I had and the device in the circuit plan. My device had 2 more ohm amps for connecting external sensors of some sort. So the old circuit plan went out of the window. And I started to reverse engineer the circuit from pictures of the PCB in Krita. Then I converted that to Kicad again, by hand. when I had the circuit plan ready, I still had some problems understanding what it does. So I went to the microcontroller forum and got some help that nudged me along the way to finding the error in this device. Some people say the sensor could be broken, but when I measured the sensor, it behaved like a normal NTC should behave. Since my measurements didn't really help and the cost of components were mere cents, I bought replacement parts for all active elements. But after switching the transistor and the ohm amps, still nothing. Turns out those 4 diodes over here create an AND function. Only if all 4 diodes have above 6 volt, the relay will turn on. With a bit of testing and probing, I found that 3 out of 4 diodes had a high signal, and if I would give a high signal to the last one, the relay would switch. But what's on that diode? Well, it's the main temperature controller. But I already had replaced that one. It has to work. So I started to think the NTC may be broken after all. So I replaced the NTC with a potentiometer and found out that if there are 0 to 16 millivolts across that potentiometer, the relay would switch when one turned on the temperature set point. 0 to 16 millivolts, what could that be? Well, that sounds a lot like a J-Type Thermocouple. Maybe not an NTC after all? It turns out the sensor wasn't an NTC but a broken J-Type Thermocouple that just happened to act like an NTC when it was broken. Luckily I had a K-Type Thermocouple laying around, so I could make a quick test. And it worked. The K-Type Thermocouple caused the temperature to be slightly off, but it proved to me that the sensor was actually the problem. So I got myself a J-Type Thermocouple. I had to remove the old one first though. After removing the heat plate, it was time for some more cleaning. The sensor itself was cemented in place. I used some high-tech tool to get it free. Then, with the help of some high-temperature silicone, I installed the new sensor. After putting everything back together, I was very happy that I made the device work again. It was a little excursion back to the days of ohm amps, where people didn't throw microcontrollers at everything. With the new parts, I hope this device will live another 40 years. And to make sure the next owner will be able to repair it again if necessary, I placed the circuit plan on the bottom of the device. If you need a circuit plan and all other useful data to this device, take a look at the GitHub page linked in the description. I hope you enjoyed this repair video. See you next time.